Now let's talk a little bit about direction fields and phase portraits. Right, so the direction field is simply the right-hand side of the differential equation. Right, so for example, so here x prime is cosine x plus sine y, and y prime equals sine x minus cosine y. So it means that for every pair x and y, we can compute the corresponding cosine x plus sine y. It's going to be the x component of the direction field, and sine x minus cosine y, it is going to be the y component of the direction field. So yeah, and then we just plot it as a vector field. Notice that again, just like for first order equations, we can plot the whole vector, so which means that the length of the arrow that we are actually plotting is proportional to the real magnitude of the vector. Or we can just forget about the length and just plot the direction. So then all the arrows are going to have the same length. Which way is better is not clear. So for example, in this case, I think plotting with magnitude is better, because there are some funny there is some funny stuff that is going on somewhere, say for example around the displays. You see that here vectors, they just have opposite direction, which looks a little bit ridiculous, and it's not clear why. But the reason why it happens is, if you look at the corresponding point in the left plot, then you see that this is actually because these vectors are very, very short, so the magnitude is close to 0. And here on the left plot, it is clear that there is, there are some large areas somewhere here and here, where the magnitude of the vector is either very small or just is 0. Sometimes, so here I don't think that there is much of a difference. So here there are only exceptional individual points where the magnitude of the vector is 0, and they are somewhere here. And I think it does matter. So here we can extract them from the right plot from the normalized one. But for a homogeneous linear system with constant coefficients, it is always easier to look at the normalized plot. The reason is because for a homogeneous linear system with constant coefficients, such a system is just x prime equals ax, where A is some n by n matrix with constant coefficients. So then, of course, if x is 0, then the right-hand side automatically becomes 0, which means that the origin is going to be a critical, well, we call it a critical point. I haven't introduced the term, but the origin is going to be a critical point. So at the origin, there is not going to be any vector. Its magnitude is 0. So, and since we know that, we can always, just expect that there is no arrow at the origin. And at the same time, if A is a non-degenerate matrix, then there is no other critical point, and then it's kind of convenient to look at the plot by just looking at the direction of the arrows. Okay, here is the definition. So the phase space of a system of differential equation is the space with where the coordinates are the unknown functions. Right? So in other words, it's not the whole, it's not among all possible variables, we exclude the independent variable. Well, a solution of a system is a vector-valued function that if you substitute it to the system as x, then you are going to get a correct equality. Right? So That's a solution of a system. Well, but then if we forget about the time, so if we just plot the solution of the system on the space x1, x2, and so on, xn, so in the phase space as a parametric curve, then it is called a trajectory. So notice that we are plotting in the phase space, which means that we are plotting it in the n-dimensional space. We do not plot time, and then it is called a trajectory. So and then a phase portrait of an autonomous system. So notice that here it is important that the system is autonomous. It is going to plot of the direction field with some sample of trajectories. A little question for you to think about is, why do we always consider phase portraits of autonomous systems, right? It is a bit philosophical in a way, but I think you can figure it out, and you are welcome to post your answers to the discussion board. All right. So let's go through a couple of examples. All right, so first, so notice that here we begin with a second-order differential equation, and we convert the second-order differential equation to a system of first-order differential equations. And then once we do this, we can construct our phase portrait. And here is the phase portrait. So it shows us that all the arrows, they kind of go around the origin, and it shows us that trajectories are closed curves. So here they happen to be just circles. How do I know it? I know it because I know how to solve this system, right? So that x is going to be c1 cosine t plus c2 sine t. So that's x. Then y, which is x prime, is going to be minus c1 sine t plus c2 cosine t. And then I can just plot a few curves like this, but it is clear that cosine and sine are periodic with period 2 pi, and then I can plot. Right? Of course, the reason why we introduced the direction field is exactly the same as why we did it for individual differential equations, right? So it is tangent to trajectories. So here is another example. So notice that now the right-hand side of the differential equation is a nonlinear function. And so here the right-hand side contains the product of x and y. So it is a nonlinear function. So this is a nonlinear differential equation. And yet it happens that trajectories are closed curves again. There is an equilibrium solution here, which happens to be x somewhere here. Equilibrium solution is when the right-hand side is 0. Of course, you can equate the right-hand side. You know, if you want to find it, you can always write 0.2x times 1 minus 0.3 y equals 0, and 0.1 y times minus 1 plus 0.4 is 0, and then you can find x, y. So x happens to be 2.7 or something, I don't know. Y is 3.2 or 3. It doesn't matter. All right, so there is an equilibrium solution. That is easy to find. I just showed you how. But proving that trajectories are actually closed curve is tricky. We are going to learn how to do it in the next lecture, I think. Well, anyway, yeah, so here is the one more example. It is very similar to the previous one, only notice that we introduced one extra term here. And because of this extra term, trajectories happen to be, instead of going around the origin in cycles, they kind of all flow towards the, sorry, not the origin, but towards the equilibrium, towards the critical point. So how do I know how to plot this and this? Is because I programmed it in MATLAB and I actually simulated it. So I can honestly, I don't think that these two systems can be explicitly solved, but we can solve them numerically and to produce a plot like this. Later, I will show you how you can solve systems of differential equations numerically in MATLAB. One more example, which is a bit maybe strange, but these things can happen too. So it is possible that there is a trajectory. So here, the trajectory is just x squared plus y squared equals 1. I am not sure if the solution is x equals cosine x and y equals sine x. Sorry, x is cosine t and y is sine t. Probably it is true. Yeah, probably it is true. It is a solution. But it is a bit funny because all other trajectories, they kind of converge towards this one. So this closed trajectory is called a limit cycle. So that is also possible, a possible